All right, this is Dynamics Review. I'm just going over what things were on the exam, and given that the average was very low on exam one, I'm just gonna review a few things I think are important. First off are just basic kinematics. Um, and this word means a lot of things, but you're most probably familiar with physics. A common one you might have seen is final position equals 1/2 at squared plus VIT plus SI. That's a very, I don't know why it's doing that. That's a very common one you see in physics, but I'm going to start off and I'm going to prove to you why you use this, what it means, and when it's applicable. So unfortunately, you can't just use this equation whenever you want. It has some level of things that need to happen. So first assumption is we're going to assume that A is constant. So our acceleration is constant. I could give you this identity, although you should probably just know these by now. But we're just assuming our acceleration is constant. So if you were to imagine some graph of time and acceleration, it would just be a flat line. And then we're going to use this identity right here. And we're going to say that A is equal to dv dt. Um, okay, and then now what, right? What we're going to do is we're going to try to get dv alone. We want to solve for v. We want some way of knowing what v is. So we're going to get v alone. So we're just going to, mathematicians will hate you, but you'll just multiply both sides by dt, right? And this will leave you with a dt equals dv. And then this is a very nice one, so we're just going to integrate both sides. And then for this integral right here, we're just going to bring out a t. And then for this integral right here, since a is constant, we're not really using bounds because it wouldn't make sense, but I don't know how else to explain that. But for v, or for a, what is it? The bounds don't really work because a is like a constant here, so we're not like driving over an area. I just wouldn't worry about it. But for v, we don't know v. V's changing. V's doing weird stuff, right? So we have some lower bound of v, which is our initial v value. We have some upper bound of v, which is our. Oh my gosh, I did this not in the way I like. I'm sorry. And some upper bound of v, which is v final. So you can imagine, um, right? I'm gonna just draw something horrible, but you have a car right here, and it's going some speed, and then you accelerate, and then you're, boop, 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 and then you have your car right here, and it's going really quick, right? Um, that's our V final, right? Then our V initial. That's a really stupid way of saying that, but I think you get the gist of it. Um, so, any integral, just dv, just gets us V out front, so we have V, and then we have that on the range of V initial to V final. And then if we um, solve that out, we have AT equals V final, so upper bound minus lower bound. And then if we just solve that for V final, we get that V final, and those three dots just mean that some processes happen, so don't worry about those. V final equals VI, because we added it to the other side. I'll just add that for your own comfort. We have V initial plus AT. And that is one of your fundamental kinematic equations, which is all wonderful and good. And then the next question is, okay, but that's just velocity. Where did where does this come from? Right? Well, what is that? Well, similarly, we're going to take this equation and we're going to put it down here. So once again, v final equals v initial plus at. And we're going to say, okay, I want to integrate both sides again. And then if we go up here, we can see that this thing right here, that our velocity is ds dt. So whenever we actually do that, we can say now when we integrate our v final, it's just going to, right, because you have your, let me try to explain this. You have your position, and if you want to integrate it, you get your velocity, or sorry, derivative. Oh my God. If you take the derivative of your position, you get your velocity, and if you integrate that velocity, you get back your position, right? So we're just doing that, and we're gonna get our final position by integrating that. This right side here, it's dt. Technically this one over here was dt too. I was just too lazy to draw it, but there we go. I'm gonna get rid of it though, because it looks confusing, but you know what I meant, right? Probably. And then that's from 0 to, I'm not even gonna put bounds on that. No bounds needed. It's a indefinite integral. There's no bounds here. So we have our final position, and then integrate that. So with respect to t, vi just becomes vit, and then at, we already have a t value, so we know that the integral of t is t squared over 2. So we have a, or 1/2. Let me just rewrite that. I'm so sorry. We have 1/2 a t squared. And then this is an indefinite integral, so we have sum plus c. In the context of this problem, though, we're solving for position. But we know we have some constant value up front, so that constant, or what's also known as our initial values, is just our initial position. Stop. I don't need those. And then if we rewrite this, we can just get that SF equals, or final position, sorry, equals, let me put this in more familiar form. Sorry, what is it doing, man? Sorry, I'm new to this. 1/2 at squared plus vi t plus initial position. So that is our kinematic equation we're familiar with. But important to note, you can, let me just, our friend now. Oh, wait, I gave that guy a cool, let me give this guy a cool outline too. Boom. Um, that's how we get our basic kinematic equations. Again, these are just derived from the definition of acceleration and velocity themselves. So these are just things that are just true based on just prior knowledge, really. Um, anyway, so just rewriting these, you have your kinematics. So when acceleration is constant, which is honestly nowadays going to be almost never, but I just want to elaborate that it's only when it's constant that you have these, and usually it's only for like a linear system too. So only if you have translational motion, rotational motion, probably not so much. But you have these equations that govern it. You have the ones we found. That's not right, man. It's just not right. 1/2 at squared plus vi t plus initial position. We also found that v final equals v initial plus at. And there's another one where v final squared equals v initial squared plus 2a delta x. Um, I could prove this one, but I don't feel like it. So that's your problem. But you could probably prove it. It's not too bad. You could do the other two, right? Um, and so again, these are true when A is constant. Now, is A always going to be constant? Not really. So sometimes one of the issues with these equations is like one, A has to be constant. That kind of sucks. Another one is if you don't have time. This one, if I can select it, this one right here is great because it doesn't have time in it. And sometimes time is our enemy. That's fun to say. But time isn't all it's made out to be. Um, so sometimes we'll need some other equations. Again, sometimes we don't have time, and that can cause a lot of issues. So one way of graphing it is to have a graph where you have your acceleration and your position. In terms of that. There's also your velocity and your position, and these have ways of relating to each other that are very helpful because, again, we don't have time. So if you know the path of something and you know some conditions of it, you can find out things about that system without needing time. I guess this being S isn't helpful because my brain says the seconds. This is S is in position. So, position. Anyway, we want to remove time from our equation. So just looking back at it, just as a reminder, we have A equals dv dt. We have V equals ds dt. And similarly, when we found the first two kinematics, and we'll find the third one here in a second, I'll be able to, I guess. I don't want to, but, whatever. Actually, I won't find it, because screw you. Um, sorry, I'm being violent today. Anyway, we'll take this equation here. So I'm looking at this, and we want to get rid of. Oh, he's back. We want to get rid of dt, and that's easier said than done, but it's not hard, and we'll see why. But how do I say this? Anyway, we want to get rid of dt, and so again, we'll just write a equals, and we want these two to separate. We want them to be of their own accord. But we need to put something here to get rid of dt. The problem is we would need some relationship here, and then whatever goes in here goes in there. So again, whatever pops up in here needs to go in here. So we need something, just something, maybe zero is not, something dt. So we need d something dt. We need something we know, or we need an identity we know that fulfills this. If you have a keen eye and you looked about an inch higher than that, you can see that we have something that's d variable dt. We have s. So let's try plugging in an s there. So ds, and I'll rewrite this so it's less evil. So we have a equals dv ds times ds dt. And we can kind of prove this out if we really wanted to. We could say these cancel out and it's still dv dt. So that relationship is still valid. But now let's take this identity right here, put that in red. It's again, this is the evil one, right? No one likes this. DSDT, and we'll take that, and we can now say an equivalent expression is still this dvds on the left here, but now this dsdt is just a v. So this gives us a equals v dv ds. But looking at this, it's not comfortable yet, right? Because we have the change in velocity with respect to the change in, or change in velocity with respect to position or whatever, right? But that doesn't intuitively make a whole lot of sense. So we don't want them together because we also can't integrate comfortably when it's like this, right? It gives us some weirdness we don't like. And we're engineers, so again, we're just gonna say screw you mathematicians. We're just gonna multiply by these, which is correct enough for us. And we're gonna now simplify this down to where now this is, sorry, I didn't explain that properly. I'm multiplying ds on both sides here because I want to get rid of this ds right here. Let me try maybe not using the same color. This ds right here or we want to get rid of, go away. There we go. We want to get rid of this. So we're multiplying both sides by ds, and we're doing that to where we're not going to have like an integral of 1 over ds. Those are nightmares. So now we're going to rewrite this to say that a times ds equals v times dv. And this is an equation or a identity you've probably seen a couple times. It's really helpful because once again, we don't have time in here. And this is great because if we know some conditions of our system, we don't even need time to figure it out. We can just say, yeah, based on initial values, we know much more things. Okay, if we take this and we're gonna just integrate both sides. Um, so we're gonna take the integral of a ds, and we're gonna go from an initial to just whatever end s value is, and that'll be equal to similarly v naught in v. So just our initial velocity value, and it's just because these match the ds there, and this matches the dv there. So you can kind of see why that works. Okay, and then if we just take these out, this gets us as. We plug in s naught. We're just going to get a s minus s naught equals, um, this is v dv, so we're going to get v squared over 2, but then we're plugging in those initial values. So we're going to get 1/2, and sorry, that's 1/2 v squared minus v naught squared. And then we're just gonna kind of extrapolate this now. We know the change, this is the change. Let me change colors here. I like the little colors. This is the change in our position, so we can say delta S. We can't really do that for these because they're a squared quantity, and there's just not, it just wouldn't work. Just trust me, bro. Just trust me, bro. But rewriting this, we get a delta S equals 1/2 v squared minus v naught squared. And then we can just multiply this 2 out to have the v's on one side. So now we have 2a delta s equals v squared minus v naught squared. And I guess I said it earlier, but this is like a final velocity, if you can live with that. And this is a final position. I'm just gonna write it because it'll make more sense. No, that's not final. Again, final minus initial. Why do you do this? Final minus initial gets us delta. I'm not going to explain that. Okay, and then we're solving for v final because we want to solve for something. So we're going to add v naught squared to both sides. So this will leave us with v final squared equals v naught squared plus 2a delta s. And let's just look around. And if you look, that is what we wrote here. I wrote s instead of x. Both just mean position. Um, this is the first problem of the exam, and I'm going to note a couple key things. Actually, let's just read it first. So, find the value of acceleration a1. So, we're going to find this value right here at this point at position s1. So, this position right here at this point. Okay. If the velocity v1 equals 7 meters per second, which is shown here, at the same position s1, sorry, let me read that a bit more fluidly. So, find the value of acceleration a1 at position s1 if the velocity of v1 is 7 meters per second. Not squared. I almost said squared. the red line tangent to the velocity curve at the position S1. It's tangent to the velocity. This is just saying your slope of this curve is S1, um, which I'm sure you know enough about slope to know what that means. Okay, so looking at this problem, there's a big thing you should notice is that um, on this axis we have our v values, which is fine and normal. But normally we're looking at like v versus t on a graph like this. Um, why am I typing? But actually, we have s here, and that is not seconds. That is position. That's meters, right? So if you notice on our graph, we don't have a time axis, which means this is independent of time, which if you haven't been asleep, you know we just found out a lot about not having time. So, if you're wondering, okay, well, if we don't have time, I can't use half of my kinematic equations. They all have time. And, well, my acceleration isn't constant, so I actually can't use any of them. So what am I gonna do? Well, if you have eyeballs, that function, um, you probably can think of what equation. So we have an acceleration graph that has the what is it, position, and we have a velocity graph where we have its slope of velocity versus position. So you can probably surmise that we can use the equation that's made for this exact scenario of ASDS equals VDV. Um, and what are we searching for? The value of A. Great. Okay, so then we have that value A here. And then now, oh my God, hold up. Cut. Sorry about that. Okay. You probably got the hint. You're going to be using ADS VDV, and we're solving for A. So, as normal, math sense will take you. I'll do this one in gold. I like the gold. As normal math sense will take you, if you're solving for something, you probably want it alone. So we're going to divide both sides by ds. It's an s. Now we have A equals V. That's horribly written. V dV ds, which is all fun and dandy. And then now we're kind of stuck because it's like, okay, well, I know this is a true statement, but how do I relate it to the tables? Well, whoa, 1, 2, 4. We know that V1, if you can even see this, V1 equals 7 meters per second. So we know V, in this scenario, is just 7 meters per second. So great, we're one step closer. Or A equals 7 dV ds. But now we need to find the dV ds term. And what does dV ds really mean? Well, it's the change in velocity over the change in position, or the slope of a velocity position graph, which lo and behold, can I zoom in? Oh, no, I can't, man. Lo and behold, though, we have our slope right there. So our change in velocity, our rise, over our change in position, our run, trying to really crank this in there, but this is our rise is 3, our run is 4, so we get, it looks like a 9. I'm gonna start putting vectors on that. We get that acceleration equals to 7 times 3/4, which is just 21 over 4 um, meters per second squared. This is the next question. I hate what this thing does. So we just discovered, actually, before going to that, let's read the question. So, car starts from rest and accelerates at a equals 0.01 s squared. Variable s is in meters, so because it's in meters, we know s is some position, until its velocity v reaches 40 meters per second. So, okay, we have a car. I'm going to just draw this badly again. And it's at rest, so we know if it's at rest that its initial velocity is equal to 0. Um, yeah, and really its initial acceleration is equal to 0. That's a weirder one, but and then it accelerates at this function right here. I'm gonna call it A1, even though I don't think it really matters, until it has reached a speed of 40 meters per second squared. Boom, boom. This car sucks. Let's give it like a really big laser. Anyway, okay. So that's kind of our initial. So let me just redraw that again. Boom, boom. It goes until it hits here. Let's keep reading the problem. And then it decelerates at a equals negative 0.1 v. So a2 equals negative 0.1 v. Where v is velocity, because it's meters per second. And then it decelerates until it stops. So this guy's going really. Let me get some big wheels on this guy. This guy's going really fast. He's all like, right? Because it was still here. It was really fast, and then it goes some distance, and it's still again. Let me get the windows in there. But we want to figure out how far did it go. So one big issue here is normally with kinematics, or when we have acceleration, velocity, whatever. There's two issues. One, we don't have time, which a lot of our equations have, so that's really sad. Also, our acceleration is not linear, or it's not constant, so that's another big issue. Luckily, in the section right before this, we found that we have an equation that doesn't need a constant acceleration, and it doesn't need time, which is this equation right here. Put it in red so you remember. You better remember this shit. Okay, so let's find the first. If you want to think about it in thermo, you can think of the first process of, and you can think of these as states, if that helps you in relating it to like what you would do in thermodynamics. But here, going from state 1 to 2, we know that it's acceleration is 0.01 s squared, or position squared. And we know it starts from rest, so it's v naught 0. Um, you can get it from this equation too, but we know that our a naught is 0, and we know our velocity it reaches is 40 meters per second. I didn't put units in the other two because I don't care. I'm sick like that. And then, similarly, again, sorry to kind of detract here, but we have three states, and kind of like thermo, you're going to find your values in one process, and then your values in another process, and that'll add up to our total distance. Um, I think that's clear, but I'll color code it a bit. We have our red process and our gold process, but to find the blue one, we need to add them together because we don't know that. If you didn't get that, please review like 5th grade English. I need it too, so don't feel bad. Anyway, we can use the ADS equals VDV equation. So subbing in for A, we have 0.01 s squared. The s equals, we got V dV, because we don't know V. And then we're gonna, I mean, you see the ds, the dv, you know you want to integrate, you know you want to. So we're gonna integrate those bad boys. Um, and then a ds, our initial position, well, we just kind of always assume we start at 0 because we like things to be easy. And then I'm gonna make my upper bound d1. I'm gonna say that this process right here is D1. Wow, that's horribly written, man. That's D1. Okay. And then for our V's values, well, we know our initial V is 0, so that's 0. We know our V at the end of this process is 40, so it's 40. So now we have our bounds. So now we just do just the classic integral stuff. We have 0.01 s cubed over 3 equals, um, why are you doing that, man? Don't want to solve that. 1/2 v squared from 0 to 40. If I just extrapolate this a bit more, we have 0.01 s cubed over 3 equals 1/2. We're going to plug in, stop trying to solve for me, man. I know what I'm doing. We're going to plug in that 40 for v, so we have 40 squared, and then we could subtract it. That's just subtracting it by 0. If you don't know why, please review 1st grade. And then we're solving for s. But really, this isn't s, this is d1. But I'm sure you understand why. It's still s, it's just our position, or yeah, it's our position at at 1 from 0 to 1, and we know that we're just going the same direction the whole time, or rather we're not like doing this sort of thing, right? To get from A to B. So we know it's that the distance traveled is the same as our position, or our displacement at this time. If you don't know why, just ask me, or just review mechanics, like high school physics. That'd be good. So D1 is 62 dot, well, that's not a dot 14 meters. Awesome. Are we done? Only halfway. So next one. Let's see. Let's get our values again. Let's reread the question because that was a lot of math. I forgot. I forgot, man. Let's see. So from the second state to the third state, we are now decelerating at negative 0.1 v, or velocities. That's our deceleration. And it does that until it stops again. And so now we have to find the distance. We'll call that d2. So let's just write down what we know. So we're going from state 2 to 3 in that process. So we know that our v1 I should have labeled this better, like, because I'm putting V1 for state 2. I'm so sorry, guys. I'm so sorry. I'm sorry. I'm not changing my ways, though. You have to deal with it. We know our V1 is, work with me, 40 meters per second. And we know our V2, it's when it stops. And if you remember, it stops. I don't know how else to say that. It stops, so it's not moving. Yes. We know our function of acceleration is negative 0 point, I forgot it, 0, 1. That's not it, is it? It's negative 0.1 v. I almost wrote the wrong thing down. That's our acceleration function. We're trying to determine the total distance the car traveled. What is it? Yeah, we're trying to find change in distance. This state we have here. Same thing as before. We don't really have time. We don't have any any love for the world, so we're gonna use ADS equals VDV. And then this time it's like, okay, well we want to solve for and we have A in terms of V, which is different, right? Because before we had in terms of S, so we could just before they were buddies because they were already helping each other out. But now they switched up on their day ones, dude. This is A in terms of V. So we want to find S once again, right? So we're gonna get A out of there. We're gonna say A switching up on their day ones. They're swapping over there. So we know that DS equals VDV over A. Awesome. Let's replace this A equation though, because we know A equals negative 0.1 V. So we can say DS equals V dV over, yes, negative 0.1 V. And again, please review basic algebra. These will cancel out. And now we are just left with ds equals dv over negative 0.1, which an equivalent statement to that is ds equals negative 10 dv. Ugh. So let's start integrating those bad boys. So we take the integral of both. Um, so let me just rewrite this down here. We have the integral of ds equals, we can bring this constant out front, so negative 10 integral of dv. And let's find our bounds. So once again, our bounds of a function, I will just draw like a little picture here. Our bounds of a function are from some spot to another. Normally, because we're engineers and we're dumb, we like saying we go from 0 to some amount. Because we like finding the change from some fixed point, which is so often 0. But in this instance, we are not starting a process, we're ending it. So instead of going from 1 to 2, we're going from 2 to 1. That's a roundabout way to say that our lower bound isn't 0, it's whatever we just ended at. So we just ended at our position being 62.14. So we're going to make our lower bound 62.14. And our upper bound is our final position. So we're our final distance. So I'm going to say D2, because I said so. Similarly with our velocity, where are we starting with our velocity? Our velocity is starting at 40 meters per second. So we're going to put 40. And where do we end? Well, we end when we're at rest. So our end limit, or whatever, man, is 0, right? So then now we just kind of take these out. We have S on the range of 62.14 to D2 equals negative 10 times V on the range of 40 to 0. And then we can just, simplify further. to just say that our total distance traveled minus 62.14 equals negative 10 times, that's just 0 minus 40. Um, Factor this out. 0 times something is 0. And we have plus 400. So we have d2 minus 62.14 equals 400. What are we looking for? The one variable, dude. Duh. So d2. Oh my god, dude, that's terrible. How do people... What? What even... Dude, never trust these platforms, bro. You know what? I'm living with that. It's good enough. Adding this to both sides, we get... Oh my god. Where are you getting hours from, dude? No. Get out of here. 462.14 meters. Boom, we're done. So just reviewing, we had a relationship of a car. It starts from rest, it accelerates, it hits a certain velocity, and then it decelerates back to rest. So, um, I'm just giving a more conceptual understanding, but we know it's not moving. It goes and goes until it hits a certain like velocity, and then it starts slowing down until it stops moving again. Because we don't have time, and also it's convenient for us, we know the identity ADS equals VdV, so we're going to use that equation. In our initial state, we have acceleration in terms of position, so we can very simply just use ADS to find set it equal to VdV. We could solve for S here. So we're just plugging in initial values. We're plugging in stuff we're going for because we know we're starting at a position of 0 and we're going to some intermittent point of this process of that function ADS. I'm just letting you know the bounds. I'm going over it again. And then for the velocity, we know that starting from rest and it's hitting 40 because that's what the problem says. So you're doing it. And then just do integral stuff. I mean, the integral stuff's the easy part. The analysis is the hard part. Um, and if you don't think so, you're wrong. Um, so that's how we found our state 2 distance we traveled, and then we're decelerating. So then, ugh, we're decelerating. So we're taking our values we're at into this state right here, since we've already traveled a bit and we're still moving. So our initial values, instead of being 0, are now some greater than 0 value, right? So, and our acceleration now, our deceleration, is not in terms of s, it's in terms of v. So we have to kind of manipulate this equation because, I mean, we'd have v ds, then we end up with like vs, and that gets nightmarish if you really want to do that. So please don't. Um, so we factor that equation out. Again, I don't like to plug stuff in right away because it's kind of harder to visualize the stuff right away. Whereas we didn't really plug anything in until really until here. So you can do a lot of the work without any numbers, which when you're in high school, man, that sounds harder, but honestly, this is easier. You don't have to think that hard. You just cross out the same number, the same letters. Ugh. Anyway, so we got this equation towards ds equals negative 10 dv. We're integrating both sides. Our lower bound of position, basically our initial value, is this intermittent point we found. Our upper bound is however or wherever we end, which ends up, our end point just ends up being our distance traveled, which is convenient. And that's going to be equal to, we found that negative 10 dv earlier, and then we know our velocity point, like our velocity conditions. Our initial condition is 40 meters per second, and then it stops when we rest. So our end condition is 0, so it goes from 40 to 0. So again, we just integrate that and we get the answer. So I hope my explanation at the end helped it out a bit. If something didn't make sense, no anger today, just sad. Okay. golf ball struck with a velocity of 80 feet per second shown. And that is, I can't do the picture. Let me do my best to, oh, it's terrible. Oh, we have colors. We can make this all pretty. All right, and we got a golf ball right there. And it is going that way. It's 45 degrees from the hill. We know the hill itself is at a 10-degree angle, which is very important. And we know that the velocity of that golf ball is 80 feet per second. And we want to find the distance of where it lands, and that's the distance relative to the hill, right? Um, and so a natural thought is like, okay, why do we care about the hill? Why don't we just tilt it? Well, if you were to tilt your frame of reference to where the hill is now quote unquote flat, gravity is acting this way, which is very odd. So we're just going to pretend like that's not true. Well, we're gonna okay, that's the wrong way to say it, but we're gonna work around it, okay? Um, I'm gonna delete this picture I drew just because the picture is right above it, just better drawn. Goodbye to my beautiful, beautiful, ugly picture. Okay. Well, we know VA, and since we don't really want to deal with uh the hill angle, we're just gonna combine them. If this is 10 and this is 45, we're just going to combine them to say that our theta relative to x is 55. And we're going to put everything in terms of that red y and that red x. The reason why we're doing it is because we want some components for our velocity values, because we're going to have an equation in terms of our y's, in terms of our x's. Eventually, we're going to have some stuff like that. And the issue we'll run into is that if we don't use these components, or sorry, if we don't account for like the hill, again, like I said earlier, gravity starts going sideways and it gets all messed up. So we're going to just use x and y to help keep everything on the same plane and keep gravity in its own equation. That way it's not messing up our lives. I hope that made some sense. Okay, so let's find our velocity of A with respect to x. So that's equal to our magnitude of A, which we know magnitude of A is 80 feet per second. But our magnitude of A, and then we're looking for x. So this is the adjacent lines, that's cosine, cosine 55. And that gets us our x component of velocity, and then our VAY. Um, if you're astute, you'll realize that it's the same idea. Okay, so now we have our velocities and our components. And what's nice is if we look at our equations, right, we have our velocities. What's our accelerations here? Well, there's no given equation for acceleration, but we live on Earth. We know this arc up there exists for a reason. Why do things fall? It is because of gravity. G. So our acceleration in these equations is just G. Howdy, howdy dowdy. So if we're solving like we are solving for this distance here along x, what we can do is we can just do our standard kinematic equations. If you remember, we have final position equals 1/2 at squared plus vi t plus si. It's something like that. That vi looks horrible. Anyway, so does the a. That's how life goes sometimes. Sometimes things are horrible. Anyways, um, let's define each term. Let's figure out what each term is, and then hopefully we can get an answer. So our S final. Well, what's the point of finding the position here? Well, we want to find distance. So we should probably put S final in terms of D. If we go to our hill example here, with a very slight, I mean, 10 degrees isn't that slight, but with a very slight hill going on here. And this is our distance D. But if we're looking um, for our final position, and we're doing it in this plane, it's not on the same plane as D. So we have to figure out the components of D. So we could say like dx, dy, whatever, but I mean, we'll just put them in terms of sine and cosine. So we know, I'll do this in green. Green makes me feel good. D, not dx. I just said I wouldn't do that. Oh my God. Well, if we're looking at the upward component, it is sine. So d sine of 10 equals, and then, okay, in the y direction, what's our acceleration? Well, it's just gravity, right? Because gravity points down toward the big Earth, where all the beautiful things in the world happen. So it's just, again, looking at this equation right here, we have 1/2 at squared, and our acceleration is gravity, so 1/2 gt squared. And then we have plus VIT. So we have to know our initial velocity. And again, remember, we're in y. I'll write that y there to remind you. We're in the y direction, so what is our initial velocity at y? Well, it's not 80 because that's just the general velocity. We have to find our y right here to know it. So it's VA sine 55, which I'm just going to write VAY. So plus VAY t, remember, because it's VIT, plus initial position, but we get to decide what initial position is, so why not just decide it's 0? Because that makes our life so easy. So I'm going to say plus 0, which you don't have to write it, but I'm just writing it for you. I'm doing this for you. Okay, x, we have same thing. We want to know this portion of d, so we're going to say d cosine 10 equals, do we have an acceleration of x? Well, we're just going to assume there's no anti-resistance. I mean, even then, golf balls tend to have very small amounts, so there's just not really an acceleration in the x. So, okay, we can say 0 for acceleration. Okay, what about our velocity? Well, looking up at here, yeah, we have some velocity going to the right. And if we look, we found it earlier, it's VA cosine 55, but I'm just going to write VAX. And remember, that is t, VAT, because it's initial velocity times t and in this equation. So it's VAT. And then plus our x initial value. But same thing with the y. We can decide where that is. So we're just going to decide it's 0 because that's a nice number. So now we have two equations. And let me rewrite them. We have our y direction, which is d sine 10 equals 1/2. Um, Technically this is negative 1/2 because we're saying g is acting in the negative y direction. So I'm sorry for that confusion, if that caused any concern. Negative 1/2 gt squared plus VAYT. Okay. And then in our x hat direction, we have that d cosine 10 equals VAX. Great. So now we have two equations. I'll say 1, I'll say 2. And we have two unknowns. We have t and we have d. Great. Um, let me, I'm looking at this. And I'm looking at this and I'm trying to figure out what they want. Oh, this is right, t. Okay. All right, so we have two equations, two unknowns. That's icky, 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 and gross. So, what are we gonna do? We're gonna solve for it. Yippee, yippee, yippee. Okay. So, let's solve for t. That's kind of arbitrary here, I guess, but um, t's a lot less gross feeling than some of the other options we got. So, I mean, hey, well, what can you do? We can say t. Right, we're just gonna look at this equation because I mean it's the easy one, right? Oh, it's the easy equation. We don't have to do as many numbers. So we can say t is equal to d cosine 10 over VAX. Which we know VAX, we found it earlier. It's VA cosine 55, and we know VA is 80. So it's 80 cosine 55, and I'll rewrite that there. An equivalent statement is d cosine of 10 over 80. Again, that's VA cosine x because it's VAX. So cosine 55. And that gets us that our t variable is related to our d variable by 0.02146d. Great. What does that mean? We found the relationship. What does that mean? Well, we can take this and we can plug it into equation one because now we can have it go from having two variables. We can replace these into there to get us with one variable. Please go away. Okay, we're done. So we're going to rewrite this as d sine 10 equals negative 1/2. And then we should plug in a value for g. So double check your units. It's feet per second. So don't get alerted. It is not the wonderful 9.81. It is 32.2 because we're in the evil world. So 32.2. If you want, you can write units to help you keep track. Feet per second squared. I'm not going to do it. Not because I'll keep track, but because, well, I have a solution in front of me and you don't. Ha! 2146. That's our time, quote unquote. It's actually our D. Let me write that a bit better. D squared. Um, Plus, we have more values here. So up here we have VAYT. We know VAY is 80 sine 55 times t, which we know is 0.02146d. So 0.02146d. And now we have this equation in terms of d. Um, I wouldn't fully recommend like trying to keep these in their values, or keep these in like their forms. You can just kind of solve out the numbers now. So we get an equation that looks like negative 0.007415 d squared plus 1.233 d equals 0. Simplifying this out, we can take d out on both sides. So we have d, and then we can make this the dominant one. So 1.233 minus 0.007415d equals 0. We have to find when d equals 0, so we know d equals 0 at 0, but that's not helpful because we knew that from the very start of the problem because we decided that was true. So this doesn't really help us. So we have to find when this is equal to 0. So 1.233 minus 0.007415d equals 0. I'm sure you know to do this, just add that to both sides, divide by the big number, or I guess it's small. It's a lot of numbers, but it's a small number, if that makes sense. But anyways, you get d equals 1.233 divided by 0.007415, and that gets you a value of 166.28 feet. Remember, because we're in the evil units. And that's our D. Um, does the question ask for anything else? No, doesn't want anything else. If you want, you could probably find like travel time. You could plug this D into our T equation earlier. You don't really need it, but if you plug it in, you get 35.68 seconds, which um that doesn't seem right. Is is this solution wrong? Yeah, no, he put it wrong in his solution. I think this is 3.568 seconds because I feel like it would cover that quicker. So let me do a hot fix here. I was just trusting the solution I was given, but the solution I was given is just wrong. I can kind of tell by just looking at it. Yep, one too many decimal places, so this is not the right value. It is 3.56. And you don't need this value, but it's a sanity check. You say, okay, it travels 166 feet and it's going 80 feet per second. Um, I know that ratio isn't exactly 3.56, but it's not going exactly straight. It's got some arc. It's wasting its time by going the wrong way, like up, and then down. So this is more of a sanity check to say, yeah, three seconds is about believable. The solution says it's 35 seconds, which I would never believe, because I mean, it's initially going 80 feet per second, right? It's not gonna like take 30 seconds. I mean, imagine like you hit something, it takes 30 seconds to go like, I don't know, like twice as far as you hit it, or at the speed you hit it. I don't know. That's funny to me. You just like hit it and it's just going, or it's like slows down. It's like almost stopped midair. That'd be dumb. Anyway, that's it for the easy chapter 12 ones. Next time I'll try to look at, I think it's chapter 16. Those ones are a bit more involved. The analysis is a bit more important. So that one is going to be probably just as mathy, but hopefully a bit less focused on like crunching numbers and a bit more focused on kind of understanding why and what you're doing. So thanks for watching. Ew, this fucking alien heart, dude. There we go. You know what? We love aliens too. With their freakish fucking hearts, dude. What is this? Should I be cursing in this? I don't know. I probably shouldn't be. Ah, it's. And then I lied to you. I felt bad. We will derive this one.